So next we'll see a case study, Vernier. So calibration of a Vernier caliper. So at an industry, somebody calibrated a Vernier caliper. So how will we calibrate a Vernier caliper? Of course, okay, we are not taken that portion. So the Vernier caliper has least count of 0.02 mm. So now again, Vernier caliper, there are several jaws, internal jaw, outside jaw. So for measurement of external dimensions, so external measuring jaws. So, and this case study is discussing only calibration at a single point, 150 mm. So the master used for calibration is a grade 1 gauge block. Actually, grade 1 is actually some different old standard. Nowadays, we say grade 0, grade, not Roman 1, it should be 1. Grade 0, 0, 0, 1 and 2. So measurement is the reading of the vernier. So what are the sources of uncertainty? What all will affect calibration of the Vernier caliper? So in dimensional measurement, the most important source of uncertainty is this is the master use. So first we start with the master. So temperature is the most important source of uncertainty in dimensional measurement because everything expands. All objects expand with temperature. So there is a temperature difference between gauge block and caliper. So gauge block will be at a certain temperature, caliper is at a temperature. If you are holding with the hand, heat will flow from your hands to the vernier and heat up the vernier. So that will cause expansion of the vernier. So it's the temperature difference which is important and not absolute temperature. Why? Because both gauge block and caliper are generally made of steel. So if both heat up by the same amount, then there will not be any dimension change, difference due to temperature. So that is why, okay, we'll discuss when we discuss dimensional measurement next chapter. So temperature difference is the source of uncertainty. Then finite resolution of caliper. So that is one source of uncertainty. Then the mechanical effects. So measurement force, how much force you are applying, alignment errors, and measurement jaw errors. So these are all mechanical effects. So measurement force, what happens? So Vernier caliper, when you press the jaws against the workpiece, so if you apply too much force, the workpiece will get compressed, so there will be some change in dimension because of that measurement force. So it should be a constant measuring force. So that's why in the micrometer we have a ratchet mechanism to make the constant measuring force. But Vernier, we don't have any ratchet mechanism or a force controlling mechanism. So this is always a source of variability and depends on the person, how much force he applies. So only with practice you will learn how to apply the right force so that you get the right measurement. So that is one problem with online lab. Although some of you have said that online lab is as better as the regular lab, but of course you can never say that you have learned swimming by seeing a video on swimming. Only when you really swim, you know what is the problem with swimming or what is the difficulty with swimming. So similarly, measurement force, how much force to apply, only when you operate the instrument you know. So you don't get a feel of that measurement force when you see a video. Then alignment errors. So how you hold the vernier. So once again, this is depends on the person. Okay, so if you misalign it slightly, there will be some difference in the measurement and the correct reading. The measurement jaw errors. So as you use the vernier, the jaws get worn out. I don't know, this is again something you have to experience. When you go to the machine shop in our, when you do the experiments on the machine shop, you will notice that all the verniers are all damaged. So you don't get any reading. So I mean, the reading all will be in error because of that. The jaws are all worn out. So instead of straight jaws, all will be bent jaws, all sorts of things is there. So these are all sources of uncertainty. So how much is the error, we don't know. So this is a source of uncertainty. So first step, okay, first is the measurement, then the sources, then the relationship between the measurement and the sources. So that is the measurement model or measurement equation. So in case of Vernier caliper, it is simply additive. All the readings are just added together. So the error of the vernier is equal to Li, the indicated length or the reading of the vernier, minus Ls, the standard length. So this is generally the formula for error. The measurement error is measured quantity value minus reference quantity value. Then corrections due to these sources of uncertainty. So standard length, okay, if it is at a correct temperature, that will not affect, but otherwise Ls into alpha is the coefficient of thermal expansion into delta T, the temperature difference between vernier and gauge block. That is the, so this much of a difference in dimension you can expect between the vernier and the gauge block. So this is the error due to temperature change of delta T. Then resolution, delta Rs, then mechanical effects, delta M. Li is the length indicated by the caliper. Ls is the length of the gauge block. Alpha is the average thermal expansion coefficient. Delta T is the temperature difference. Delta Rs is the correction due to finite resolution. So first, we have a mathematical model relating the measurement result to all the sources of uncertainty. So measurement results, so what we are trying is to find out during calibration is what is the measurement error in the vernier caliper. Okay, measurement error or minus of that error will be the correction for the caliper. Okay, delta M is the correction due to all mechanical effects. Sorry, I forgot this. Okay, so this is understood. So error is measured quantity value minus reference quantity value. Then these errors, how, depending on how you define them, it can be plus or minus. Okay, so let us assume it is all plus. And anyway, in uncertainty, when you take root sum of squares, sign does not matter. So it does not matter much here what sign you take. Okay. Okay, so next step is to estimate the uncertainty due to each source. So now we have got identified all the sources of uncertainty. Now we need to identify the uncertainty due to each source. So repeated measurement. So you measured the gauge block several times. Measured value obtained was 150.1 mm and there was no variation. So there is no repeated readings, there was no variation. All the readings were 150.1 mm. So the uncertainty due to repeated readings is 0. So uncertainty in the length indicated. The indicated length is the reading. The repeated readings, there was no uncertainty. All showed same reading. So because, I mean, okay, unless there is a wear which is non-uniform, it will not be like this. So sensitivity due to Li is 1, anyway it is material. Then Li minus Ls. So next term is the length of the standard, that is the length of the gauge block. So gauge block grade 1, gauge block is used, is mentioned. So its uncertainty is specified as 0.1 micron, plus or minus 0.1 micron in the calibration certificate. So what is this? Is it a combined standard uncertainty or expanded uncertainty or coverage interval? Okay, so 0.1, nothing is mentioned. So if nothing is mentioned, we generally choose this as the expanded uncertainty. So is there a correction for length of the gauge block? No. Nominal length of the gauge block is used without any correction. So sometimes the gauge block may have some error as given in the calibration certificate. In that case, that value has to be taken. So it is specified as plus or minus 0.1 micron in the calibration certificate. So let us assume it to be the expanded uncertainty with 95% confidence. Okay, so this is only an assumption. It may not be true. Anyway, just to illustrate various sources. So in real life, that is a problem. Many times information is not available, and then we have to decide whether we should take it as normal distribution or uniform distribution or triangular distribution. So for test, it is easy because it will be given in the test that you have to choose uniform or triangular, or you will be given sufficient information. For example, if you are told that the output is a digital reading, then we know that it should be uniform or triangular, or the difference between two digital readings should be triangular. So based on your information, you have to determine the distribution. So here, plus minus 0.1 micron, so we can assume it to be uniformly distributed. So uncertainty in the standard length, so that is the length of the gauge block, is A by 1 by, okay, 1.96 is actually required, but there's not much difference between 1.96 and 2. So practical purposes, 1 by 2 is enough. But for the exam, I'll expect you to use 1.96. So 0.1 by 2 is 0.05 micron. So this is the standard uncertainty. So first step is to get all the standard uncertainties. Then sensitivity. So that is the partial derivative of error with respect to Li. So since Ls minus Li, that is minus 1 is the sensitivity. The coefficient of sensitivity of the error with respect to the standard length. Then effect of temperature. So there the coefficient of thermal expansion comes into play. So how much is the temperature difference, the delta T? So equal within plus or minus 2 degrees Celsius. And okay, since we say it's maximum, we can assume it is to be uniformly distributed. So average thermal expansion coefficient is 12 × 10⁻⁶ per degree Celsius. So uncertainty in this is assumed negligible because this is 10⁻⁶, and the variability in this will cause a very small change in the correction. So standard uncertainty of delta T will be A by, so plus or minus 2 uniform. So uniform distribution means standard uncertainty will be A by √3. So 1 by √3, 1.15 degrees Celsius. And sensitivity with respect to delta T will be partial derivative of Ls alpha delta T with respect to delta T, so that will be Ls alpha. So Ls is 150, alpha is 12 × 10⁻⁶. So this is the coefficient of thermal expansion for steel. So that is 0.0018 millimeter per degree Celsius. This is the sensitivity of the reading to changes in temperature. Next is finite resolution. So least count is 0.02. So why we are considering this way? Because the repeated readings, if it is smaller than this, then we will not get any uncertainty. But actually it may be anywhere between the two divisions of the vernier. So least count of the vernier is 0.02. So we can assume this to be uniformly distributed. It can be anywhere between this plus or minus 0.01. So that is, so standard uncertainty due to resolution will be A by √3 again, 0.00577 mm. Then sensitivity will be partial derivative of delta S with respect to, sorry, partial derivative of error with respect to delta S. That will be 1. So that is the effect of resolution. Then mechanical effects. So the maximum possible variation in deflection due to variation in the force applied. was calculated using theory from strength of materials and estimated as plus or minus 0.005 mm uniformly distributed. So the maximum possible variation. So you calculate using strength of material. You know the force, how much force you are applying, how much is the variability in force. Say what is the force that your hand can apply. Say maximum maybe 200 grams or 2000 Newton. So for that, what will be the deformation in the gauge block or vernier? So that calculate using strength of materials. We learn this type of calculation later, chapter on dimensional measurement, how to compute the errors in dimensional measurement. So there we learn this into more detail. So anyway, that's why the answer is given, plus or minus 0.005 mm uniformly distributed. So this also is assumed uniform. Okay, this is uniformly distributed is the assumption. Okay, if you feel your normal is better, you can take that. But the worst is uniform. So that's why many times if you have a doubt, generally you take uniform. So 0.005 by root 3 is 0.0029 mm. So sensitivity of delta m is 1. So all sensitivities are 1, it's just additive. Correlation, assume that none of the input quantities were considered to be correlated. So we neglected all the correlations. So now we prepare the uncertainty budget. So first column is the variable or quantity, then its estimate. So Li is the indicated length, the reading. So there is no variation in the repeated reading, so 150.1. The standard length is 150. Delta T is the temperature difference. So standard uncertainty is 1.15. Sensitivity is alpha. Okay, we have already calculated that. Then quantity delta res. Uncertainty estimate is 0. Standard uncertainty is 0.00577. The delta m uncertainty is 0.0029. Then, so the error estimate is Li minus Ls 0.1. And then these contributions we have calculated. We have to add root sum of squares of all these contributions to get the standard uncertainty, combined standard uncertainty. Okay. So this would have been done in class. I would have closed this and asked you to do it in class. Then expanded uncertainty for normal distribution, assuming again 2, not 1.96, since not much difference between that. So for practical purposes, it doesn't matter. Since anyway we need only 2 digits, significant digits for the uncertainty. So remember, but in between steps you have to have more digits. Why? Because when you take the difference between 2 quantities, for example, regression and all, we take EI equal to YCI minus YI cap, YI minus YCI, YI minus YI cap. So then, if both quantities are big, the significant digits, the answer will be much less. So, expanded uncertainty is this much. Coverage interval will be plus or minus this. Okay, 0.1 plus or minus 0.014 mm with 95% confidence. So, it's a 95% coverage interval for the error in the Vernier caliper. So this is how we do an uncertainty analysis for a particular experiment. So that is something which we have to learn. So any experiment you do, any measurement you do, you have to compute the uncertainty and report it along with the measurement result. So that is an important requirement. Okay, so as per the standard. So because nobody else can tell you how good was your measurement. Only you know what was the what was the situation in your measurement. So the estimated uncertainty of the measurement should be given by you when you give the measurement result.